Hello class, I made a lecture video for this lesson because I saw that the counterpart lecture video in Math 23 is super long and I myself don't watch lengthy lecture videos, so here I am. And without further ado, let's study limits and continuity. So do you still remember how we solve limits of functions in single variable? Sometimes we just plug in the value, and if we get a real number, then that's already the limit. What do we do when we don't get a real number? We transform the function first. Sometimes we factor first the function, cancel terms, then we evaluate. Or we rationalize first, cancel terms, then finally evaluate. These ideas would still hold when we have functions of two variables. For our example 1, suppose we want to evaluate the limit of 2 plus y squared over xy minus 2x squared, which is a function in two variables, as x comma y approaches the point negative 1 comma 0. So first, let us try to just plug in the values x is equal to negative 1 and y is equal to 0. If we plug in, we have 2 plus 0 squared over negative 1 times 0 minus 2 times negative 1 squared. This is equal to 2 over 0 minus 2, which if we simplify further, we get negative 1. Since we have a real number, therefore, negative 1 is already our limit. We want to evaluate the limit of x raised to 4 minus y raised to 4 over x squared plus y squared as x comma y approaches the origin or the point 0 comma 0. If we plug in the values x is equal to 0 and y is equal to 0, the function will become 0 over 0. This is not a real number, therefore we have to transform first our function. Note that we can write x raised to 4 minus y raised to 4 as the product, x squared plus y squared, and x squared minus y squared. Just copy the denominator, and now we can then cancel x squared plus y squared. So we are left with x squared minus y squared. And thus, if we evaluate now, x is equal to 0 and y is equal to 0, we get 0 as our limit. Now for our third example, we want to evaluate the limit of x squared plus y squared all over 2 minus square root of x squared plus y squared plus 4 as x comma y approaches the origin. Again, if we plug in x is equal to 0 and y is equal to 0 to our function, we get 0 over 0. Therefore, we have to transform first our function, but there is nothing to factor here, and so we rationalize since we have a square root in the denominator. The conjugate of the denominator is 2 plus the square root of the same thing all over, write again the conjugate. And so if we multiply the denominator, we have 2 squared, so that would be 4, minus the square of the square root, so the whole radicand x squared plus y squared plus 4. And for the denominator, just copy first the factors. Now, if we can see in our denominator, we have 4 minus 4. We can cancel this. And so we are left with negative x squared plus y squared in the denominator, which we can also cancel with x squared plus y squared in the numerator. So we are left with negative 2 plus square root of x squared plus y squared plus 4. And I think this time we can now just evaluate. So plug in x is equal to 0. And y is equal to 0. And if we do that, we have negative 4 as our final answer. Before we move on, please answer first these exercises. Pause the video and ask in the group chat if you encounter problems in solving these limits. One way to show that the limit of f of x does not exist is to show that the left-hand limit of f of x is not equal to its right-hand limit. How about if we consider now f of x comma y? Do we still consider limits from the left, from the right, or now we have from above, from below, along this diagonal path, or along this random curve? There are a lot of options now. If we can find two distinct paths or curves c sub 1 and c sub 2 such that the limit of f of x comma y along the curve c sub 1 is not equal to the limit along the curve c sub 2, then the limit does not exist. For the example 1 of part 2, let us show that the limit of x squared minus y squared over x squared plus y squared as x comma y approaches the origin does not exist. So to show this, let us consider the paths. Let us say y is equal to 0. And let us also consider the path x is equal to 0. Note that the path that we should consider must always pass through the point 0, 0, the point where we are evaluating our limit. Now let us solve the limit of x squared minus y squared over x squared plus y squared along c sub 1, or along y is equal to 0. Since we are on the line y is equal to 0, we can just directly substitute y as 0. So here we have x squared minus 0 over x squared plus 0. And since our function now is only of the variable x, we can simply write the limit as x approaches 0. We can disregard y now. So then we now have a limit of a function of only a single variable. And note that we have x squared over x squared, so if we simplify, that is just 1. And the limit of 1, the limit of a constant, is itself. So the limit is equal to 1. Now how about the limit along the path c sub 2, or along the path x is equal to 0? The limit as x comma y approaches the origin along the path x is equal to 0 of x squared minus y squared over x squared plus y squared is equal to the limit of, so here let us substitute x as 0. So we have 0 squared minus y squared over 0 squared plus y squared. And now we have a function of a single variable y. So we can simply just write here y approaches 0. We can disregard x now. And if we simplify our function here, we have negative y squared over y squared, or simply negative 1. And the limit of the constant negative 1 is itself negative 1. And since these two are not equal, therefore, the limit does not exist. For our next example, let us show that the limit of x raised to 4, y raised to 4, all over x squared plus y raised to 4 raised to 3, as x comma y approaches the origin does not exist. For this, let us take the path x is equal to 0. Note that first we are always considering the easy paths. So x is equal to 0, y is equal to 0, y is equal to x. So the limit along c sub 1, or along x is equal to 0. This means that we can now substitute 0 in x. So we have 0 raised to 4, y raised to 4, 0 squared plus y raised to 4 over 3. As y approaches 0, here we have 0 over y raised to 12, or we can simply write the limit of 0. Okay, let's just write 0 over y raised to 12. But 0 over y raised to 12 is simply 0, and the limit of a constant is itself. The limit is equal to 0. Okay, now for the next step, I will just leave it to you to verify that the limit along y is equal to 0 is also 0. The limit along y is equal to x is again 0. And similarly, the limit along y is equal to negative x is also 0. So we really have to try to find a different curve c sub 2 such that the limit along c sub 2 is not 0. Let us observe our function, in particular in our denominator. In our denominator, x has degree 2, but y has degree 4. Maybe I can take x is equal to y squared so that x squared will be equal to y raised to 4. And so I can add it with the y raised to 4 on the other term. I can also consider x is equal to y squared because I am sure that it passes through the point 0, 0. Consider x is equal to y squared. Again, just a reminder, all the paths that we should consider must pass through the point 0, 0, the point where we are evaluating our limit. So we already have x is equal to 0, that is the y-axis. Y is equal to 0 is this one, the x-axis. Y is equal to x is this diagonal. Y is equal to negative x is this diagonal. And x is equal to y squared is this parabola. If we now take the limit of our function along the path, or along the curve rather, along the curve x is equal to y squared. So let us substitute y squared to every x. Y squared raised to 4. Copy y raised to 4. Y squared raised to 2 plus y raised to 4 all raised to 3. Now this is a function of a single variable y. So we now have y approaches 0 here. We can disregard x. Let us simplify first. We have here y raised to 2 raised to 4. So let us multiply exponents. We have y raised to 8. For our denominator, same. Let us multiply the exponents 2 and 2. So we have y raised to 4 raised to 3. Now, for our numerator, let us add exponents. So 8 plus 4, we have 12. For our denominator, we have 2y raised to 4. Y raised to 4 plus y raised to 4. That is 2y raised to 4. Then let us take the cube. So 2 raised to 3, that is equal to 8. Y raised to 4 raised to 3, that is equal to y raised to 12. We can cancel y raised to 12. And so we have the limit of the constant 1 over 8, which is itself 1 over 8. And since the limit along c sub 1 and the limit along c sub 2 is not equal, then we are now sure that the limit does not exist. Now it's your turn to try solving these exercises. Again, pause the video and ask in the group chat if you encounter problems in solving. First, we recall that a function f of x is continuous at x is equal to a if the function value of f at x is equal to a is defined. Second, if the limit of f at x is equal to a exists. And if the function value is equal to its limit. If one of the three conditions are not satisfied, then we say that f is discontinuous. In the case where f is discontinuous at x is equal to a, if the limit exists, we say that the discontinuity is removable. If the limit does not exist, then we say that the discontinuity is essential. Similarly, we say that the function f of x comma y is continuous at the point a comma b if the function value f of a comma b is defined. Second, if the limit of f of x comma y as x comma y approaches a comma b exists, and these two, the function value and the limit, are equal. Otherwise, we say that f is discontinuous at the point a comma b. And again, if the limit exists, the discontinuity is removable. If the limit does not exist, the discontinuity is called essential. For our first example, here in part 3, we want to know if the function 2 plus y squared all over xy minus 2x squared is continuous at the point -1, 0. So first, let us evaluate the point -1, 0 in our function. So let us solve first for f of -1, 0. Just plug in the values 2 plus 0 all over 0 minus 2 times 1. We have 2 over -2, or simply -1. Now let us solve for the limit. We already solved from part 1, example 1, that the limit is also -1. Therefore, since the limit is equal to the function value, we say that f is continuous at the point -1, 0. Now for our next example, is f of x comma y equal to x raised to 4 minus y raised to 4 all over x squared plus y squared continuous? Lastly, for our example for part 3, is the function x squared minus y squared over x squared plus y squared continuous at the origin? Clearly, f of 0, 0 is undefined. So we are already sure that f is discontinuous at the origin. We already showed from part 2, example 1, that the limit of f as x comma y approaches the origin along the path y is equal to 0 is not equal to its limit along the path x is equal to 0, which then implies that the limit does not exist. That is, the limit of f as x comma y approaches the origin does not exist. And since the limit does not exist, we now say that f has an essential discontinuity at the origin. Thank you for watching until the end of the video.